Hello, everyone. I'm very excited to be here virtually, even if I couldn't be here in the flesh, as it were. I did take the advantage of not being able to attend the conference to move house, scale out from a 3 to a 5-room apartment, and observe the lunar eclipse that was, so the solar eclipse that was on Tuesday. And I think very much what I am is someone who's very interested and passionate both about site reliability engineering and about astronomy and space. And that is the thrust of my talk here and what I'm going to be talking about. My day job is at IBM, where I'm an SRE architect in the internal CIO organization, basically helping us manage our own internal cloud platforms more efficiently and more reliably. When I'm not doing that, I've been writing and talking quite a bit about SRE lessons from space exploration, moon landing, Challenger, International Space Station. I talk about it, I write about it, and this is the inspiration for today's talk about the James Webb Space Telescope. If you're interested in science and technology, you probably haven't been able to avoid hearing about it over the last few months. And what I'm going to talk about is what we as SREs can learn from the Webb Space Telescope and the engineers who designed it. This is a part inspirational, part aspirational session. So we're going to start off with, why did we develop Webb in the first place? This is what we already had, the Hubble Space Telescope, which did fantastically. Why did we need a new space telescope? And there are two main reasons for that. The one is the non-functional requirement that Hubble is a telescope from the 90s and it's getting old and needs to be operationally replaced. But that's not the reason NASA invested $9 billion in a new space telescope. The reason was the functional requirements. What is Webb going to do that Hubble cannot? And the picture you see on the screen here is called pillars of creation. These are gigantic clouds of gas, which are stellar nurseries. Inside this gas are stars being born. But Hubble, seeing in a specific wavelength, can't see these stars inside, can only see the gas clouds. Webb, and this is a brand new picture, which was published just last week, just in time for the conference, sees in a different wavelength and essentially has X-ray vision to see into the gas clouds, to see the stars in the process of being born. So this is very much the way that our clients, the developers, are creating new products in order to give our organizations more capabilities. And as I'm talking, my examples are going to be, of course, from Webb, but I want you to consider how all these things map to your own organizations and the own relationships and checks and balances you have with the requirements of your clients. So let's look at the functional requirements of Webb and how they affected the non-functional requirements, the things that we as site reliability engineers have to deliver. And one of the principal concepts in Webb is that it's going to be seeing further back in time, closer to the beginning of the universe than Hubble did. So this is our business KPI. This is how we know that Webb did a good job. And this means that Webb has to see in the infrared wavelength. This is what the developers have to do. This is the new product that they have to create. Seeing as it's in the infrared, it has to be colder. It has to run in a different operational environment than Hubble did. Just like we are developing something that needs to be more scalable, more flexible, then it has to run in the cloud and can't be on bare metal. Being colder means it has to have precise temperature controls. These are the operational controls that we have. Hubble orbited Earth, meaning that every 90 minutes it got cold or got hot, depending on whether it was the shadow of the Earth or in direct sunlight. Webb has to have a stable temperature, which means that it has to have a remote orbit far away from Earth, and excuse me, and it has to have a sunshade so it's permanently in the shade. So this is our non-functional requirement. The scientists don't really care where it is. They don't really care whether it has a sunshade or not. But we as SREs now know that we have to develop Webb in a certain way. Another thing is the capacity of Webb. We want to be larger than Hubble and have more capacity to collect light in the same way that whatever business product that we create has its own KPIs of driving more business and so on. So this means we have to have a physically larger mirror. But the mirror is going to be too large to be launched in a single rocket, no matter how large the rocket is. That's our operational constraint, which means that we have to develop a foldable mirror. All these things mean that Webb is going to be very, very complicated to deploy, very, very complicated to operate, just because of the functional requirements. So, in fact, Webb does not orbit Earth, does not orbit the sun, but it flies in a very strange location called L2, which means it's always just behind the Earth and facing the sun. This means it's in a stable position from a certain perspective and can constantly be shielded from the sun. So just 1 second. To illustrate something of what I'm talking about, let's assume that this is the size of the mirror that we need to create. And the mirror is just much too large to be built on Earth. So what do we do? So this is our monolith. So instead of building a monolithic mirror, we're going to take a series of microservices. Each of these has the same capacity as the mirror, but it's just smaller, doing a specific thing. And what we're going to do is we're going to build a larger mirror built out of these smaller mirrors. So you can imagine each of these being a microservice, and this plate here being the platform on which it works. So this is not I got a bit sick of paper, so I've got another model here for you, made out of Lego, showing the 18 mirrors that Webb is built out of. Here we have the secondary mirror where all the light is collected. The light comes here, collected in these mirrors, reflected into the secondary mirror, then into the camera and camera system here. So this is all the business of Webb. So what is this part? This is the heat shield of Webb, and this is the main computer of Webb and the communications disk sending information back to Earth. So Webb flies like so through space, where over here is the sun and the Earth. It always points in this direction, and we always have to take a picture at about 90 degrees to the angle of the Earth, which means that, for example, Webb can never take a picture near the sun. Now, I built this model, but this model is Webb as it is today. How was Webb launched? We can't fit this gigantic thing in a rocket. What I have here is a small model of the Ariane 5. Obviously, these are not to scale, but I'm going to take this rocket, and I want you to use your imaginations that this is the part of the rocket. This is where Webb is. And we've got another model here folded up where it fits. So imagine this being our CI/CD pipeline, where Webb is launched into space, comes out of the rocket, and then it has to unfold. The mirrors unfold like this. The secondary mirror extends like this. And now just imagine that everything that I'm doing here is part of the CI/CD pipeline of source to image, testing, deployment, getting through all our tests that we need to be sure that it is deployed correctly. And of course, this model, while it is more complex than this model, because it has moving parts, it's smaller. I don't have everything here. I don't have the heat shield, for example, which also unfurls, simply because of complexity. And this just goes to show us that if we want something to be to withstand all our non-functional requirements, we're adding a lot of complexity for something that essentially is not going to be needed after we have successful deployment in the case of Webb. So now that we've seen that we've deployed something so complicated with so many moving parts, somewhere so remote and distant, how did we get here? How did we get to the position where we had to do something so complicated? And the history of Webb is a very, very long history. It starts off with the legacy observatories that it came to replace: Hubble, Spitzer, Chandra, various other space telescopes, where NASA decided we needed something newer to replace them. The next generation space telescope started off planning in 1995. The projected budget was going to be about $1 billion. By the time we reached 2003 and began the high-level design, there was an understanding that all these functional requirements would lead to a lot of non-functional developments. Over 10 technological breakthroughs were necessary in the manufacture and operations of Webb in order to succeed in the deployment. Sorry, in the development and deployment, and the plan was for $1 billion for 10 years of operations. 2007 to 2021, detailed design and construction, and the costs ballooned up to $9.5 billion just for the manufacture, launch, and another $1 billion planned for the first years of operations. Why so much? Because of the non-functional requirements, because it had to work perfectly, because we had to launch it and we could not send astronauts to do any repairs like we did with Hubble. There was no way of fixing any mistake. So it has to be self-repairing, it has to be reliable, it has to be perfect on the first try. Initial deployment of the mirrors, there were problems. Initial deployment of the heat shield, it tore. So all these tests happened on Earth, and it takes time to, okay, let's redesign, let's fix, let's do it. Very much waterfall development. December 2021, it was launched from French Guinea on an Ariane 5 rocket. And in July of July of this year, it became fully operational and started delivering results down to Earth. So where did the trust come from? How did NASA gain the confidence to launch Webb, to spend these $9.5 billion, where any single mistake would mean that the whole project is a complete failure? So the trust comes from experience, from previous missions. One way that NASA usually tries to reduce risk is redundancy, sending multiple spacecraft. Most famously, perhaps, are the Voyager spacecraft, which recently celebrated 45 years in space. I don't think there are many hardware systems that are operational with no upgrades whatsoever for over 45 years. And they visited the planets Jupiter, Saturn, Uranus, Neptune, and are now exploring interstellar space. More recently, we have things like the Mars rovers, which deployed in pairs. And even closer to home, satellite constellations, either GPS, Starlink, other communications satellites, where you have built-in redundancy because you're not depending on the success of a specific satellite to deliver the content that you need. One of the problems, however, especially with unique systems like Webb, is that when you have an underlying problem, redundancy doesn't help you. There have been cases where the space probes were developed using alloys, metallic alloys that just didn't survive for long enough, so both components failed together. Or maybe there's an underlying dependency, like we have DNSs. It doesn't matter how many containers or VMs or whatever you have, if they're all using the same database, they're all using the same DNS, the system will fail. So that's where repairability comes in. And of course, the most famous repaired solution is the Hubble Space Telescope, which has been repaired multiple times and upgraded during its career. But also, what a lot of people don't know is the International Space Station itself is constantly being repaired. About 50% of the time the astronauts spend on the station is just keeping the station working. Now, repairability is something that we're used to doing back in the monolith days. Today, we often try to not repair a component, but to replace it and do an upgrade in place with a bug fix using using our deployment mechanisms. We don't fix a container, we replace it with a new version which works better. Again, in the case of something like the Webb Space Telescope, when one costs $9.5 billion, you can't just build another one with a fix and replace it. So there's actually nothing to be done except to invest in reliability and look at every single component and subcomponent of Webb and make it as reliable as possible, invest in the engineering of these components. But again, NASA has been doing this often enough, and with enough space telescopes that they have the techniques of how to build something reliable, and they just used it on a much larger scale than before. And despite all this investment, decades and billions of dollars and tens of thousands of man hours invested in reliability, we still had a lot of points of failure. Just for the deployment of Webb, the unfurling of the various components and positioning them in place, they identified 344 single point of failure items, which they could not avoid. And what they did is just prioritize these, add tests, add tests, add tests, and add tests. And that's how they generated the confidence that they needed in the solution. And sometimes these tests require compromises. I showed you the two sides of Webb, one side with the scientific instruments and the other side with the operational components. These might be two completely different spacecraft. One is required to be at a precise temperature of minus 233 degrees, and the other one is protecting the other side. Now, one of the questions I often heard when Webb was first launched is, why is there no selfie camera? Now, we're used to seeing when astronauts do spacewalks, we're used to seeing them walk. And that's not only is it a pretty picture, it's also something that mission control uses to see that they're working in the right direction, they don't have a problem, they can help them if something goes wrong. Or in the launches, for example, of SpaceX rockets, you can see the launch, you can even see the landing. So why doesn't Webb have a selfie camera? Obviously, this would help engineers diagnose problems. And this is where we have the compromise between the functional and non-functional requirements. Let's say we want to have a selfie camera here pointed at the telescope itself. It can show us everything that's going on. Well, the problem is that this camera in and of itself is generating heat, which means it's disrupting the activity of the camera of the space telescope. So we'd have to do something like shield the camera so that it doesn't spread heat. But this means we've got to put up a camera, we've got to add the shielding. This is adding weight. We're already at the limit of what we can send into space into the right position, because that's a non-functional requirement, maximize our science. So if we're adding the selfie camera with the shield, that means we've got to take out a scientific instrument, or we've got to take out the fuel in Webb, which means that it will last for longer. So we can't do this. Maybe we can put the camera on the hot side of Webb and then make a little hole or something in the heat shield so it can still observe without generating the heat. But we've just made a hole in our heat shield. So again, this isn't a good solution. Going round and round and trying different things, eventually a decision was made, no selfie camera. We'll just have to double down on other mechanisms of collecting observability information, such as more telemetry, maybe more instruments, maybe adding instead of having a camera which can tell us how the various things are positioned, we'll just add a sensor behind the back of each thing, which will tell us, of each component, which will tell us its precise position. We're adding a lot of complexity, but we're reducing any impact the non-functional requirements has on the functional capabilities of the telescope. But there's a cost to that. It's a lot more design work. We're getting perhaps slightly lesser telemetry information upon which to operate, and so on. But then again, in the case of Webb, which is a once-in-a-generation instrument, this compromise is justified. So Webb went into production in July, and it was launched in December, had a 6-month period of testing. It went into production in July. Already by May, we hit our first reliability issues, where Webb was hit by a large meteoroid flying through space. When I say large, I mean a speck of dust. But this was much larger, I think by nearly an order of magnitude larger than what engineers and scientists had predicted would hit Webb. Webb was designed to withstand a lot of impact from meteoroids. It was hit by 3 small meteoroids previously, which had absolutely no impact on the telescope. But you can see here, one of the mirrors was slightly unbalanced by the impact of the meteoroid, which means that they had to adjust it in place. So let's look at how this looks. This is part of the report that the engineers gave after finalizing the remediation process. And I'll zoom in here so you can see the interesting thing. So every part of Webb is well managed, is well measured. So this is the performance of the mirror. A low number is a good number. So this is the SLA. This is what the engineers promised the scientists, that they would deliver a telescope which is accurate to 150 nanometers. This is the SLO. This is what they actually set out to design to create, at least 125 nanometers. And this is the actual result of Webb, somewhere under 75 nanometers. So Webb was over-engineered in a good way, in the fact that it is delivering better quality science than was required by the scientists, and better quality science than the engineers thought that they could achieve. As a result of the impact of the meteoroid, there was some degradation, this paler blue color, but as you can see, it's still well within both the SLO and the SLA. So the management here of the problem was good enough that we can say that there's no functional problem with the meteoroid impact, even though they are still investigating how they can reduce the problems, the potential problems of future such impacts. So this wasn't quite a black swan event where something completely unexpected happened. This was an event that was expected, but the scale was larger than expected. So they set up a number of post-incident reviews and committees to try to see what would happen in order to avoid such situations in future. Another reliability issue, which occurred recently in September, this is an illustration of the mid-infrared instrument, which is one of the cameras on Webb. As you can see, what it does is it collects various streams of lights and makes the measurements. One of the components here is a grating wheel, which is used to focus the light in the right way. And what they discovered was that during the focusing process, there's more friction than expected. More energy is needed in order to engage the mechanism. Once it succeeds in getting into proper position, then the scientific information is completely normal. and there's no impact to that. This is similar when we talk about the golden signals to a saturation message. Now, the system is working properly. We don't have any errors. Latency is well within the numbers that we want, but it's making more of an effort than we think it should be making. So we're running out of some resource. In this case, the resource that we're running out of is the flexibility of the focusing wheel. So again, what they did here was they shut down this specific focusing wheel, to not because there's a problem at the moment, but because they want to spend more time investigating, because they want to be sure that that the extra friction doesn't cause the component to wear out faster, which will cause errors, latency equivalent in future. So we've gone down to a degraded state where 16 of the 17 instruments are functioning perfectly, and one of the instruments is under investigation, not because there is a problem now, but because we have seen a signal of a potential problem, and we want to make sure it doesn't develop into a real problem at any time in the future. Another example of something we can learn from the space telescopes, I'm calling this a type of chaos experiment. As we know, one of the principles of chaos engineering is that we're going to create hypotheses of how our system works, a model of what the system does, and then challenge this hypothesis using a chaos experiment in order to gain confidence. Either we found out that our hypothesis is correct and the model works, the architecture is as we thought it was, or we found out that it's incorrect and now we can make corrections in order to gain confidence. And what they did back in 1995 was direct Hubble at a blank spot in space, take a long exposure picture and see what can we see. And what they found surprised them. They expected to find some galaxies there, but they found a lot more galaxies in this bland black spot of space. And the galaxies were of a different configuration and formation than they expected, which means that they had to change the models of galaxy creation. And just like in a chaos experiment, we want to scale out, as we gain confidence, we scale experiments out, and we go from tests to staging to production, or larger areas of production for our experiments. Again, one of the plans for the James Webb Space Telescope was to improve on these chaos experiments and to go even deeper into deep space than Hubble has done. So just to coming up to the end of my session, I've identified a number of items which I call the SRE strategy that the Webb engineers used. They needed 100% availability for success. They only had one opportunity to launch Webb. They wanted to achieve the best possible performance and reliability, even beyond the SLA that they promised. They needed to prioritize non-functional requirements with functional requirements, observability requirements with the benefits that they had. A lot of redundancy was invested in here, and of course, a lot of lessons were learned from previous missions. But the thing is that most of us are not creating a $9 billion machine, which is a once-in-a-generation technological marvel. Most of us are working to keep our systems working as efficiently as possible, as usefully as possible, as reliably as possible, but reliably as possible down to our requirements, which are not 100%. So a lot of these things are things that you should be inspired by, but not aspire to. Do not aim for 100% availability in the real world, because again, unless you're developing something like Webb. To summarize what I think the SREs should take from Webb, and I'm using a much larger font so it's easier to read, is just redundancy of our systems. And we also need to remember that redundancy does not replace reliability. Repairability of our systems or replaceability of our subsystems, and of course, reliability throughout every service as much as possible. So if you only remember 3 words out of this whole session: redundancy, repairability, and reliability. That is my message. This is what I would like us to learn from Webb. I've included a couple of links here. The European Space Agency is central to the Webb project. If you don't like Lego, you don't want to invest in the Lego model, there's a paper model you can buy. IBM, I'm very happy to say that IBM has been working in the space tech ever since there was a space tech back in the 1950s. And if you're interested in what I'm doing in the CIO internal cloud, we have a Medium blog where we talk about what we're doing. And of course, if you're more interested in the space aspect of it, I've got Medium articles that I've been publishing, and I will continue to publish. So thank you very much, and please feel free to reach out to me.